orbiter reached Mars after traveling through space for more than 9 months. At exactly 9 hours, 0 minutes and 46 seconds, universal time, its main engine started. The burn was meant to slow the spacecraft so that Mars could capture it into orbit. A few minutes later, the spacecraft passed behind the planet. Controllers expected its radio signal to disappear temporarily. But the silence began 49 seconds earlier than predicted. When the spacecraft should have returned from behind Mars, no signal came back. There was no final photograph, no emergency message, no confirmed explosion. A spacecraft that had crossed hundreds of millions of kilometers had simply vanished. The orbiter had been built to study Martian weather, dust storms, and the atmosphere. Before it could begin, it needed to enter a carefully calculated orbit. The most important number was its closest distance from Mars, called periapsis. The planned altitude was about 226 kilometers. That gave the spacecraft a reasonable safety margin above the atmosphere. But during the final week, new calculations placed the spacecraft lower. First, between 150 and 170 kilometers. Then, about 1 hour before arrival, possibly as low as 110 kilometers. The estimate was moving in the wrong direction. Why did each new calculation bring the spacecraft closer to danger? The answer was connected to a small routine operation repeated throughout the journey. Mars Climate Orbiter used spinning reaction wheels to control its direction. Sunlight and other forces slowly added momentum to those wheels. To release it, the spacecraft fired small thrusters. Each firing was tiny. Imagine walking while someone repeatedly taps your shoulder. One tap changes almost nothing, but hundreds of taps in the same direction can move you far from your original path. Navigation engineers therefore needed an accurate record of every thruster firing. Software on Earth calculated those forces and stored the results in a data file. The numbers looked normal, but the mission depended on what those numbers meant. For the first months of the journey, the navigation team already had problems using these files. Some contained formatting errors and incorrect spacecraft orientation information. By April, the obvious problems had been corrected. But another difference appeared. The forces written in the files seemed smaller than the movement detected through radio tracking. This was an important clue, but the effect was difficult to measure. Many thruster firings pushed the spacecraft sideways relative to Earth, where radio tracking was less sensitive. There were also gaps between the teams that developed the spacecraft and those operating its navigation system. The warning existed. Its cause remained unresolved. The problem became more serious because Mars Climate Orbiter fired its small thrusters much more often than expected. Its one-sided solar array allowed sunlight to build momentum quickly. The spacecraft performed these momentum release firings roughly 10 to 14 times more frequently than navigators had anticipated. Every event added another small modeling error. By September, engineers performed the final planned trajectory correction, called TCM-4. It was supposed to place the spacecraft on the safe 226-kilometer approach. But the later estimates continued to fall. A final emergency correction, TCM-5, was discussed. It might have raised the spacecraft's path, but it was not fully prepared, tested, or supported by clear decision rules. The mission was already entering its orbit insertion sequence. TCM-5 was not performed. After the spacecraft disappeared, investigators returned to the small thruster data. 6 days later, they found the difference. The ground software produced the thruster impulse in pound-force seconds, but the navigation system expected Newton seconds. One system used an imperial measurement. The other expected a metric measurement. No conversion had been applied. A pound force is equal to about 4.45 newtons. So the navigation system counted less than 1/4 of the real effect of every small thruster firing. The digits were not corrupted. The physical meaning of the digits was wrong. Imagine one company weighing a package in pounds, while another reads the same number as kilograms. The number 20 remains 20, but the understood weight is completely different. That was the first domino. One program did not follow the agreed unit. Another program trusted that it had. Testing did not catch the mismatch. Each thruster firing moved the spacecraft more than the navigation model recorded. Because the firings happened far more often than expected, the difference accumulated across the journey. The false trajectory passed through software checks, team handovers, unexplained tracking differences, and the final planned correction. After applying the correct conversion, investigators reconstructed the spacecraft's real path. Instead of passing 226 kilometers above Mars, it probably passed at about 57 kilometers. The mission team considered about 80 kilometers the minimum survivable altitude. Mars Climate Orbiter was therefore around 170 kilometers lower than originally planned. At that altitude, it entered the Martian atmosphere far too deeply. The original investigation said the spacecraft may have been destroyed in the atmosphere, or damaged and thrown back into orbit around the Sun. Its exact final moments were never observed. But the cause of the loss was clear. The official investigation identified the unit mismatch as the root cause, but it also found a larger system failure. Software testing was incomplete. Communication between teams was weak. Navigation warnings were not fully resolved. The emergency correction was not ready to use. Independent checks failed to expose the growing difference between the model and reality. This is why the lesson is not simply use the metric system. The required metric unit was already written in the specification. The real lesson is to verify that every system produces what the next system believes it is receiving. A number carries more than digits. It carries a unit, a definition, and an assumption. Mars Climate Orbiter's engine worked. Its radio worked. Its computer followed its commands. The mission was lost because different parts of the system did exactly what they had been told to do, while disagreeing about what one number meant. A tiny measurement error became dangerous because the surrounding system allowed it to remain invisible. That is the pattern behind the butterfly file. A small detail, a chain of ordinary decisions.